In the last section, we studied diatomic molecule vibration, and the solution to the Schrödinger equation of harmonic oscillator give you allowed energies that is determined by quantum number n. So h divided by 2 pi square root k over mu n plus half. And these energy levels are equally spaced. Okay, the absorption of light can only take place between adjacent energy levels. Because these energies are equally spaced, and therefore there's only one frequency that will be absorbed. The absorption between n equals 0 to n equals 1 is called fundamental absorption, and this absorption is in the infrared range. Now, in reality, molecular vibration deviate from harmonic oscillator, and so enharmonicy has to be added. And because of that, the absorption may take place between 0 to 2. And this is called the first overtone. Although the intensity may be very weak. And you may also see 0 to 3, and that is a second overtone, and it becomes even weaker. So now, in this section, we are going to talk about rotation of molecules. First, we go over classic mechanics. So in classic mechanics, rotation, the equations of the rotation resembles those equations in linear motion. For example, in linear motion, kinetic energy is calculated by half mv squared. So here, for rotation, m is replaced by moment inertia defined by this equation. M mass times r squared. R is the radius. Okay, the linear speed v is replaced by omega, the rotation angular speed. Okay, and therefore the kinetic energy is half I omega squared. Now the linear momentum is m times v. So m is replaced by moment inertia, and v is by omega, and therefore you have this equation. Angular momentum equals I times omega. And we also know that in linear motion, kinetic energy is half mv squared. Also, you can write p squared divided by 2m. So we can write p is replaced by linear momentum by angular momentum, m by I. And that's why you have this equation. Okay, L squared divided by 2m. Just like linear momentum, angular momentum is also important in rotation. For example, when athlete rotate, the angular momentum must be conserved. Okay, so when we want to rotate fast, okay, you pull arms in, and that will reduce the radius, rotational radius. This will decrease the moment inertia. And since angular momentum is conserved, when the moment inertia becomes smaller, the angular speed becomes faster, and therefore you rotate fast. Now when you want to slow down, you pull out your arms, and that will increase the radius, increase the moment inertia. And again, because angular momentum is conserved, when the moment inertia is increased, the rotational speed will become smaller. Diatomic molecules are two-body system. Just like in vibration, two-body problem can be reduced to one-body problem if the reduced mass is used. By doing that, the equations of kinetic energy of angular momentum are the same as in one-body system, except when we calculate the moment inertia. Okay, we should use mu reduced mass instead of individual atom. Just like vibration in diatomic molecule, rotation of molecules must also be treated by Schrödinger equation. And the Schrödinger equation for rotation in 3D is shown here. The reduced mass, the kinetic energy operator, second order derivative against x, y, z. And where is the potential energy operator? Now, if we assume the bond length of diatomic molecule doesn't change, the R is a constant, then the potential energy is 0. And so we don't have a potential energy operator if in rigid rota approximation, where bond length doesn't change. In addition, due to the center of symmetry, this equation is most convenient to be solved using spherical coordinates. So instead of using x, y, z to represent a point in a three-dimensional space, we can use r, theta, phi, these three variables. Now r is the distance between origin and the point, okay, of the 3D space. Theta is the angle between z direction and the line from origin to the point of the 3D space. Now this line projection to xy plane, you have a new line, okay, this line, all right, is the projection of from origin to the point, to the xy plane. And the angle between this line and the x direction, this angle is called phi. Okay, so if we know r, theta, phi, then the point in the 3D space is defined. So we can use r, theta, phi to represent any point in the 3D space. So how is these two coordinates are related, x, y, z, r, theta, phi? The equation is z equals r cosine theta, x equals r sine theta, sine phi, and the y equals r sine theta, sine phi. Now using these three equations, the Schrödinger equation in x, y, z coordinates can be converted to sphere coordinates, and that's this equation. So in this equation, instead of derivative over x, y, z, we have derivative over theta and derivative over phi. Now where is the derivative over r? Well, in rigid rotor, r is constant, so r doesn't change. The derivative is 0. Okay, so now you only have two variables. Essentially, we change Schrödinger equation from x, y, z, three variables to two variables, theta and phi. Okay, because r is a constant. So the wave function now includes only two variables. Both are angles, and this kind of wave function is called the spherical harmonics. The goal now is to solve the Schrödinger equation to find the spherical harmonics and allowed energies. Here is the Schrödinger equation for rigid rotor in spherical coordinate. The wave function can be written as a product of two functions. One only contains theta, one contains phi. By doing that, the Schrödinger equation can be separated into two equations. One contains phi, one contains theta. Now, these two equations are not independent. They are both equal to ml squared. ml is a number that to be determined. Now solution of this left side gives you the function of phi. And it is found out that ML can only have certain allowed values. These are 0, positive, -1, positive, -2, and go on. In other words, a quantum number ML comes out from this equation. And so the function of phi is determined by quantum number ML. Now the right side, the second equation, already includes this ML, and therefore the function of theta must be also determined by ML, quantum number ML. However, when solve this second equation, another quantum number, which is labeled L, comes out, and the L can only be 0, 1, and 2, and keep going. Now these two quantum numbers, ML and L, they are not independent. For example, L can be 0, then ML can only be 0. ML is determined by L. So when L equals 1, then ML can be 0, positive, -1. That's all. When L equals 2, then ML can be 0, positive, -1, positive, -2. In other words, the maximum ML is L. So in general, L can be 0, 1, 2, 3, 4, keep going, and ML can be 0, positive, -1, positive, -2, until positive, -L. And therefore, the total wave function is the product of two functions. Okay, one contains theta, one contains phi, and you have two quantum numbers, quantum number ML and the quantum number L. We're going to see in the next slides. Here shows the first few spherical harmonics, or the wave functions of the rigid rotor. These functions all contains two quantum numbers, L and M. For example, when L equals 0, M can only be 0, and therefore you only have one wave function, and that is square root 1 over 4 pi. Now when L equals 1, M can be 0, positive, or -1. So you have three possible M values. And the combination of these two give you three wave functions. For example, here shows L equals 1, then M can be 0, or M can be positive 1, or M can be -1. And that gives you three wave functions. Note that these functions, they have variables theta and phi, theta, phi. Now sometimes you have only one variable theta. Now when L equals 2, you have 5 possibilities: 0, positive, -1, positive, -2. So the combination of these two give you 5 wave functions, and they all have L equals 2. L equals 2. But the M can be 0, here, 0, positive 1, -1, positive 2, and -2. So 5 wave functions. Again, this wave function contains the variable theta and phi. We have seen a few examples of wave function of the rigid rotor, which are the eigenfunctions of the Hamiltonian operator. But what about the eigenvalues? Eigenvalues are the allowed energies. And here is the allowed energies. And it's interesting to see that the wave function is determined by two quantum numbers, L and M. But the energy is determined only by quantum number L. Now we know that in linear motion, energy it can be written as P squared divided by 2m. P is the momentum. In rotation, we write as L squared divided by 2I. And L is the angular momentum. So compare these two equations, it suggests that h bar squared times L plus 1 might be related to L squared. It turns out that it is true that L in rigid rotor is calculated by h bar times square root L times L plus 1. Now the symbol here represents the magnitude of angular momentum. Now angular momentum is a vector. It has direction, it has a magnitude. So this equation tells us that we only know the magnitude. We only know the magnitude. We are not sure about the direction of the angular momentum in rigid rotor. We're going to see this more in the next slides. In the last slides, we showed that we can calculate the magnitude of angular momentum, but we don't know the direction. It turns out that we actually know the z component of angular momentum. Z component of angular momentum is determined by quantum number m. M can be 0, positive 1, negative 1, until positive L, negative L. And the z component of angular momentum is calculated by m times h bar. Now, for example, if L equals 2, from last slides, we know m can be 0, positive negative 1, positive negative 2. So you have 5 z component. Now let's calculate the angular momentum magnitude. The magnitude is calculated by h bar times L plus 1. L here is 2, so 2 times 2 plus 1, and that gives you square root of 6 times h bar. So this is the angular momentum magnitude, and we have 5 z component. So how do you visualize it? Here is a diagram that can help you understand this. Now this shows 5 cones. All these cones, they have the same magnitude here, and the magnitude are all h bar times square root of 6. That's the angular momentum value, okay, magnitude. But the direction can be here or here or here. You don't know x, y direction, but they all have the same z component. Here is 2, okay, z. So here is a positive 2. So the z component is 2 times h bar. So 2 times h bar. Okay. Now for this second cone, the z component are all positive 1, and so the z component angular momentum is 1 times h bar, and then the third cone is 0, and the fourth one, all right, is negative 1 times h bar, and the last one is negative 2 times h bar. Okay, although we don't know the x-y direction, we know the z component. Okay, the orientation of rotation is quantized. Now this can be simplified as a 2D drawing. Okay, in this drawing we show 5 orientations. Okay, 5 orientations, and their z components is precisely known, which is negative 2, negative 1, 0, positive 1, positive 2. Those are quantum number m, then times h bar, give you z component. Sample question. Treat the rotation of hydrogen iodide as a hydrogen atom rotating around the stationary iodine atom. This is a good approximation. as iodine atoms is so heavy, it hardly move. What this means is that the two-body system hydrogen iodide rotation can be treated as one body, just hydrogen attached to iodine center. Okay, so hydrogen rotate, and this is because iodine is much heavier than hydrogen, so iodine doesn't move under this approximation. So the consequences, when we calculate the moment inertia, we, instead of using reduced mass, okay, for a two-body system we use reduced mass, but here we only use hydrogen mass because iodine under this approximation doesn't move, and then times the radius here, the bond length, okay, squared. Now in this equation, the bond length is 160 pm. Pm means 10 to the minus 12. So 160 times 10 to the minus 12 is 1.6 times 10 to the negative 10 squared. And the mass here, first we find the molar mass of hydrogen atom, but in this equation, this mass should be the mass of one atom, okay, individual atom. So we have to divide by Avogadro's number, and the this is grams per mole, so we need to change it to kilogram. So you need to divide by 1000 to become kilogram, and by doing that you get this number, 1.67 times 10 to the minus 27. Now you can use this as a conversion factor in the future to convert 1 mole grams to 1 atom or 1 molecule in kilograms. So here it gives you 4.289 times 10 to the minus 47 kilogram as the moment inertia. Okay, so the question is, evaluate the energies of degeneracy and degeneracies of the lowest 4 rotational energy levels. Now the rigid rotor approximation quantum mechanic calculation gives you allowed energy levels that determined only by quantum number L. Okay, that's the conclusion from the previous slides. So these are the allowed energies for rigid rotor. The bond length doesn't change, and that give you allowed energy levels. I just calculated, so plug in, and so we get this equation. All right, so if we know L, we can calculate allowed energies. So for the first 4 lowest rotation energy level, the L allowed L can be 0, 1, 2, 3, and so plug in those numbers. Okay, so for the first one, L equals 0, lowest energy is 0. Okay, now what's the degeneracy? Well, when L equals 0, M can only be 0. Okay, again, that comes from previous slides, the relation between L and M. So M can only have one value, and so the combination of L and M can only have one possibility, that is L equals 0, M equals 0. That determines one wave function, and therefore the degeneracy is 1. What about L equals 1? So when L equals 1, plug in this equation. All right, this is the answer, the energy. Okay, so with this energy, how many wave functions has this energy? Okay, when L equals 1, M can be 0, can be positive 1, can be negative 1. Okay, that's the allowed quantum number M when L equals 1. So in other words, you have 3 possible M. So the combination of L and M give you 3 possible wave functions. For example, it can be L can be 1, M can be 0, L can be 1, M can be 1, L can be 1, L can be negative 1. each of these combination give you a wave function. Okay, and therefore the degeneracy is 3. Okay, you have 3 degeneracies. Now what about L equals 2? So when L equals 2, again plug in this equation, the energy, allowed energy is this one, and the M can be 0, positive, negative 1, positive, negative 2. So the maximum M is L, and so positive, negative 2. So you have 5 possible M, and the combination with L give you 5 wave function, and therefore the degeneracy is 5. So 5 wave function, same energy, because energy is only determined by L. But the wave function is determined by 2 quantum numbers, L and M. So you have 5 wave function. All right, same energy, so degeneracy is 5. Similarly, L equals 3. This is the allowed energy, and the degeneracy is 7. Okay. Lastly, what is the frequency of a transition between the lowest 2 rotational level? So this is the lowest, this is the energy above it, and the transition between these two. Okay, you calculate the delta E, which is just this energy, and this equals h times frequency of light. So the frequency of light should be the delta E divided by Planck constant. Okay, so should be delta E, but in this case, lowest energy 0, so it's just E, which is 2.6 times 10 to the minus 22 divided by Planck constant, and that's the frequency of the light that will be absorbed. All right, and it turns out that this energy is in the microwave range. Okay, as we mentioned in the last section, rotation energy levels falls in microwave range, which is much lower than the vibration energy levels. What's the significance of the quantum number M and the quantum number L? Let's compare 2 wave functions. The first one, L equals 1, M equals 0. The second one, L equals 2, M is 0. So we choose 2 wave function that has the same M but different L. All right, and let's plot it. Okay, so these are the plots of the wave function of these 2 wave functions, and you can see they have different shape. Okay, and that tells you angular momentum quantum number L determines the shape of the wave function. Now the angular momentum quantum number, as we see before, determines the magnitude of the angular momentum. Okay, it's h bar times square root L plus 1. Okay, so that's why it's called angular momentum quantum number, because it determines the magnitude of angular momentum. Now the energy of rotation is also determined by this quantum number. So 2I h bar squared L plus 1. Okay, so the angular momentum quantum number determines the magnitude of angular momentum, the energy of the rigid rotor, and here we show it also determines the shape of the rotation. Okay, now you may find that the shape of these 2 wave function reminds you the atomic orbital of hydrogen atom. For example, the left side looks like a p orbital, the right side looks like one of the d orbitals. Indeed, when we solve Schrödinger equation for hydrogen atom, the solution contains a wave function that resembles the rotation, okay, the spherical harmonic, and we have 3 quantum numbers when we solve hydrogen atom, but the 2 of them are the same as here is quantum number L, quantum number M. They have the same significance, and that is the quantum number L determines angular momentum of hydrogen atom, And the quantum number m, as we will see in the next few slides, determines the orientation or the z component of the angular momentum. And in chemistry, we define L, all right, as when L equals 0, we call the s orbital. When L equals 1, we call the wave function p orbital. And when L equals 2, the wave function is called the d orbital. And the 3 is f orbitals. Having looked at the quantum number L, now let's look at the quantum number m. We choose 3 wave functions, same quantum number L equals 1. M can be 0, positive, negative 1. So 3 wave functions, all right, L equals 1, M equals 0, L equals 1, M can be positive, negative 1. So 3 wave functions, and when we plot them, and they give you same shape because they have same quantum number L, but they orient differently. Okay, quantum number L tells us the magnitude of angular momentum. It doesn't tell us as the direction. So here, the quantum number m gives us more information of the direction of the angular momentum. So the shape tells you the orientation, different orientation. When L equals 1, in chemistry, we call p orbital. So here, you have 3 orientation. They call px, py, pz. Okay, so the quantum number m gives you more information about angular momentum. Only certain directions are allowed. Okay, and it determines the z component of angular momentum. And here it tells you the orientation of the wave function. Now remember, these 3 orientation, they have the same energy. They all have the same energy because the energy is 2I h bar square L plus 1 times L. Okay, so the energy is only determined by quantum number L, no matter what is quantum number m. Okay, so you have 3 possible m, but they have the same L, and therefore they have the same energy. They are degenerate. And so when we draw energy level, so these are the 3 energy level that has the same energy. They are degenerate. However, if you apply magnetic field, okay, so for example, you apply magnetic field in one direction, then because these 3 wave function has different orientation, they interact with this external magnetic field differently, and therefore now the energy becomes different. So they separate. Okay, so they have different energy now. Okay, and this tells you, and therefore quantum number m also tells you the energy in the external magnetic field. All right, and that's why this quantum number is sometimes called magnetic quantum number. Okay, so when an external magnetic field is applied, energy along this direction will split, and that's called magnetic quantum number. Here are some examples of possible L and M. The smallest L can be 0, and the possible M can be 0. And the wave function is s orbital. You only have one wave function. Now when L equals 1, M can be 0, M can be 1, M can be negative 1. So you have 3 combinations. They call Px, Py, Pz along 3 orientations. And when L equals 2, M can be 0, positive, negative 1, positive, negative 2. So the combination of L and M give you 5 orientation. So they call d orbital with different orientation. And when L equals 3, M can be 0, positive, negative 1, positive, negative 2, until positive, negative 3. That's 7 orientations. And these are the 7 f orbitals. Let's focus on the allowed energies and calculate the frequency of light that can be absorbed by rotation. Previously, we showed that the energy of rotation is determined by quantum number L. Scientists prefer using quantum number, a symbol J instead of L when calculating the frequency of light that can be absorbed. Now, it doesn't matter which symbol do we use. The energy is calculated by h bar squared divided by 2I, the quantum number times quantum number plus 1, and the quantum number can only be 0, 1, 2, 3, 4. Now, h bar equals h divided by 2 pi. So the square of it should be h squared divided by 4 pi squared. And therefore, the energy is h squared, you can write as h times h, divided by 4 pi squared times 2. That's 8 pi squared. And then times I, and then j plus 1. So this is equivalent to this equation, the allowed energies. All right, now to simplify this, notice that here these are all constant, so we can combine all constant together and give one constant. But instead of combining all of them, scientists prefer to combine one h Planck constant divided by 8 pi squared times I, and also divided by a speed of light. Okay, so combine all the constant, but only one Planck constant, and divide by speed of light and give a name B called rotational constant. And the reason to do that is, one, to simplify this equation, and also you will see more clearly in later when we calculate the frequency of light, it becomes much simpler. Okay, so by doing that, the allowed energy now is h, because you still have one h here, times the constant b. Now in definition of b, you have the speed of light. So here we don't, so we need to times the speed of light, and then j plus 1. Okay, and therefore this is the new equation to calculate the allowed energy levels using rotational constant b. Okay, rotational constant. Now, how do we find the frequency of light? We need to find the energy separation between adjacent energy levels. So let's say at J, okay, this is the energy. So what is the energy at J plus 1? Okay, you plug in this equation, replace J by J plus 1. So that will be H, B, C, and J becomes J plus 1. And here J plus 1, and then plus 1 is J plus 2. Okay, so this is the energy at J plus 1 level. The delta E is using J plus 1 energy minus J energy. Okay, so notice that both of them has HBC. So you can write HBC, and both of them has J plus 1. J plus 1. So you times J plus 1. And then the energy at the J plus 1 level, you have J plus 2. And then in at the level J, you have a J here. So J plus 2 minus J equals 2. So that's the energy separation between energy level J to J plus 1. Okay, and therefore that's the in general, the delta E is 2 HBC times J plus 1. And it is important to notice that the separation between adjacent energy level is determined by J. You have a J. Now remember, in vibration, harmonic oscillator, okay, you have energy levels, and when we calculate the energy difference, they are all the same. They are h times natural frequency. There's no quantum number in it. In other words, it doesn't depend on quantum number. They are all the same, and therefore the consequence is you only see one a frequency that can be absorbed, because the separation are the same. So here we show that the energy separation depends on J. So at a different energy level, the separation is different. You can see in the diagram, the separation becomes larger and larger. All right. So the separation is not uniform, and therefore you expect to see many frequencies that can be absorbed. So different frequency of light can be absorbed by rotation. So a series of allowed energies denoted by quantum number J, and they are not equally spaced. The selection rule for a rigid rotor rotation is similar to the harmonic oscillator vibration. For example, here it says the delta J must be positive negative 1. That means the absorption must take place between adjacent energy levels. For example, this is J equals 0, J equals 1, J equals 2. So the delta J must be positive or negative 1. So that's only between adjacent levels. That's similar to the vibration. Now, so the first one says, for a molecule to give a pure rotation, it must be polar. And this is slightly different from vibration. Now, in vibration, it says the dipole moment must change during vibration. For example, if we're talking about hydrogen, so the hydrogen is symmetric. So when they vibrate, the dipole moment doesn't change. It cancels each other. And so hydrogen molecule does not absorb light when vibration. Okay. Now rotation says it must be polar. So hydrogen molecule is not polar, and therefore hydrogen molecule does not absorb light for rotation. Okay. Also, however, when we talk about CO2, okay, CO2. This is a symmetrical molecule, so it's non-polar, and therefore this does not absorb light in rotation. Okay, because rotation must have a polar, so this doesn't. However, when vibrate, one vibration mode is, for example, the left band goes to this side, and the right side also goes this side. And when they do this mode vibration, the dipole moment change, even though it's a non-polar molecule. Okay, the dipole moment change, and therefore CO2 can absorb infrared, all right, but it cannot absorb microwave in rotation spectrum. We just show that for rigid rotor, the allowed energy levels are not equally spaced. The separation between two adjacent energy levels is calculated by 2hbc times j plus 1. B is a rotational constant. In order to calculate the frequency of light, we let this equal to h times frequency of light that will be absorbed. Okay, and Planck constant cancel each other, so the absorption frequency will be 2bc j plus 1. Okay, and that is in the unit of hertz. If we want to calculate the frequency in terms of inverse centimeter, we divide by speed of light, and that cancels the speed of light, give you 2b times j plus 1. Now looking at this equation, you can see that when you change j, the absorption frequency will change. So with many possible j, we predict that there will be a series of absorption lines that are expected. And those because the separation is in the microwave range, so the absorption will be in the microwave. Here Here again shows the allowed energy levels that are not equally spaced, and the predicted frequency of light that will be absorbed is 2 BC J plus 1 in terms of hertz. So how does the absorption spectrum look like? Well, the first frequency that will be absorbed is when J equals 0. So 0 plus 1 is 1 times 2 BC. So the first absorption frequency is 2 BC. 2 BC. So at 2 BC frequency, a line is absorbed. And then the next one is when J equals 1. 1 plus 1 is 2. 2 times 2, 4 BC. So 4 BC. You see another absorption line. All right. The next one is J equals 2. So 2 plus 1 is 3. 3 times 2 is 6. So at 6 BC, you see another absorption. All right. And keep going. 8 BC. Okay. So this is how it looks like. The first one is J equals 0. And then 1, 2, 3, 4, 5, 6, 7. Okay. So some students may wonder, in this case, why when J equals 7, the absorption intensity is the highest absorption. Okay, the reason for that is at the room temperature. Okay, because the energy separation of rotation is very small, so the thermal energy is enough to occupy many of these energy levels. So most energy level can be occupied. However, there's a distribution, and in this case, J equals 7. That energy level has the highest percentage of molecules that occupy this energy level. So because this energy level has the highest percentage of molecules, and therefore when they absorb light, give you the highest intensity compared to other energy levels. Another important thing to notice is that the separation between adjacent absorption frequency is here is 2 BC, and this one is also 2 BC, and here 2 BC. So all of this separation has a separation 2 BC between adjacent frequency of light that will be absorbed. Okay, now that's in hertz. Now in inverse centimeter, you divide by speed of light, and that gives you 2B. So in other words, the separation between these two adjacent frequency is just 2B. Okay, and this is interesting because the rigid rotor energy levels are not equally spaced. All right, the energies depends on J. The separation increase. However, the frequency of light that will be absorbed, all right, has a uniform spacing. All right, and the spacing is just 2B in terms of inverse centimeter. And that is very useful information, because if we can measure this absorption spectrum, we can measure the separation. We find the 2B, and then we find the B. B is the rotational constant, and the rotational constant is equals h Planck constant divided by 8 pi squared c times I. Okay, so we know Planck constant, we know speed of light, and therefore we can find the moment inertia. So by measuring speed of the spectrum, we find the B. Using this spacing, we find the B constant, and then we can calculate the moment inertia. And the moment inertia equals the reduced mass times bond length squared. And therefore, eventually, we can calculate the bond length. Okay, so let's go over the vibration. So vibration, you have a uniform spacing, and so you only absorb one frequency of light, which equals the frequency equals h divided by 2 pi square root k over mu. And so by measuring the absorption light, okay, you measure the frequency of light, and you can calculate the force constant. Force constant measures the strength of light, strength of the bond. So it's a triple bond, it's a double bond, the strength are different, and that can be found by the K constant. Okay, so measuring the infrared, which is for vibration, and you can find the K constant. But by measuring microwave, which is for rotation, we can find the B constant, and then we can find the bond length. So by measuring microwave spectrum, the rotational constant can be calculated, which leads to the bond length calculation. Example. To a good approximation, the microwave spectrum of hydrogen chloride consists of a series of equally spaced lines. So this is absorption line are equally spaced. Okay, and the separation is this number. Okay, in hertz. And it asks you to calculate the bond length. Okay, we just showed in the last slides that the absorption frequency separation is 2bc in terms of hertz and 2b in terms of inverse centimeter. All right, so please pay attention to the unit. In this case is hertz, so this should equals to 2bc. Okay, so 2bc should equals to 6.26 times 10 to the 11. Okay, and the b is h divided by 8 pi squared speed of light times moment inertia. So we can calculate the moment inertia. All right, just modify this equation. The moment inertia can be calculated, and the answer is 2.68 times 10 to the minus 47 kilogram meter squared. Okay, now in order to calculate bond length, okay, the moment inertia is mu times r squared, so we need to find mu, the reduced mass, and the reduced mass is m1 m2 m1 plus m2, and so in this case is chlorine is 35, hydrogen is 1, and so you use the molar mass times conversion factor to change to one molecule, the mass in kilogram. Okay, and that gives you 1.61 times 10 to the minus 27 kilogram, and then you calculate the bond length. Okay, and that gives you 1.29 times 10 to the minus 10 meter. Summary of quantum mechanics rigid rotor. Now, rigid rotor is the case when the bond length doesn't change. The solution to the Schrödinger equation shows that the wave function is determined by two quantum numbers. Quantum number L, which is called the angular momentum quantum number, and the quantum number M, which is called the magnetic quantum number. Now, L determines the energy, allowed energies of the rigid rotor. It also tells you the magnitude of the angular momentum. And the angular momentum quantum number also tells you the shape of the wave function. The magnetic quantum number tells you the z component of angular momentum. So it tells you the more information of the orientation of the wave function. Now, from this equation, we can show the energy are not equally spaced. And therefore, you would expect the absorption of light contains a series of lines. And this equation, the frequency of light absorbed is 2bc times j plus 1, or 2b times j plus 1 in terms of inverse centimeter. So both is determined by j quantum number. So the frequency of light change when you change J constant, J quantum number. Now, it is interesting that the absorption of light frequency is actually equally spaced. And this spacing is 2bc in terms of hertz, or 2b in terms of inverse centimeter. And therefore, by measuring this absorption, which is in the microwave range, then we can find the B constant. And from B constant, we can calculate the moment inertia, which we can calculate the bond length of the molecules. So far, our discussion is based on rigid rotor model, where the bond length doesn't change. In effect, when molecules rotate, there's a centrifugal force that's trying to stretch the bond out, and this will increase bond length. Increase bond length, increase moment inertia, and which increase the rotational constant. So in reality, the molecular rotation is not strictly rigid rotor, and the Schrödinger equation has to be modified. So this is the rotational energy that take into account the centrifugal distortion. So the first term comes from the rigid rotor, and the second term is the centrifugal distortion. Okay, the D is called centrifugal distortion constant, which is affected by rotational constant and also vibration frequency. So how does vibration affect the distortion? So when molecules vibrate, when the bond vibrate, and this essentially distort the bond length. A bond that easily stretched means you have a small force constant. A small force constant will give you a small vibration frequency. So this is vibration frequency. Okay, small k, small vibration frequency, and the small vibration frequency, larger rotation, centrifugal distortion constant. Sample question. Calculate the centrifugal distortion constant for carbon monoxide, assuming the rotational constant in terms of centimeter is 1.9313, and the vibration frequency is 2170 inverse centimeter. So the equation to calculate a centrifugal distortion constant is 4 times B cube divided by frequency second power. So plug in the data. The answer is 6.116 times 10 to the minus 6. And this is a very small number, particularly if you compare with rotational constant. So that means the centrifugal distortion is a very small effect, have a very small effect on the energy levels. The rigid rotor model works fine in most cases. Now let's come back to the question we asked before. If a harmonic oscillator model predicts that only one frequency is observed in infrared spectrum, and this is the prediction by harmonic oscillator, so when you do infrared, supposedly you see only one frequency absorbed. Okay, but in reality, when we do infrared for carbon monoxide, for example, we see a broad absorption. Okay, this is a very broad absorption. In fact, there's a missing peak in the center. So if you have a high resolution, you actually see many, many small peaks. Okay, so why is that? The reason is when molecules vibrate, molecules also rotate. And it's because of the rotation that cause this broadening of this energy absorption. And we're going to see more in the next slides. Here is the equation to calculate allowed vibration energy levels. And sometimes we use symbol V to represent the quantum number, but here we use N. And this is the equation to calculate the rotational energy levels. In this diagram, this represents the classical mechanics potential energy, half kx squared. But quantum mechanics says the only allowed energies are described by this equation. So when you plot, the lowest energy is n equals 0, and then n equals 1, n equals 2, n equals 3, and keep going. So the transition of vibration energy level should be between these lines. Okay. However, when molecules vibrate, molecules also rotate. And so the allowed rotation energy level is described by this equation. And when you plot, here is the allowed rotation energy levels when the molecules vibrate at the lowest energy level. Now, when the molecules vibrate faster, so it goes n equals 1, molecules also rotate, and these are the allowed rotational energy levels at the second vibration energy level. So think about a two-story house. So you have stairs. So these are the stairs belongs to the first floor, and these are the stairs belongs to the second floor. So when the electrons jump from low energy to high energy, it's not between just between n equals 0 to n equals 1. Instead, it's between the stairs. So the stairs of the first floor to the stairs of the second floor. So you can see there's many possible transitions between these stairs. Now, if you enlarge this diagram, okay, you get this one. Again, these are the rotational energy levels when the vibration are lowest, n equals 0. And these are the rotation energy levels when the vibration has a higher energy level, n equals 1. So all these transitions happens between n equals 0 to n equals 1. So delta n is 1, and that obeys the selection rule for vibration. Delta n has to be positive, negative 1. So in this case, n equals 0 to n equals 1. Now, what about rotation? So let's look at this first transition here. So this transition is between j equals 11 to j equals 10. Again, delta j in this case is 10 minus 11, that's negative 1. Okay, now the selection rule of delta j. Selection rule says delta j has to be positive, negative 1. So in this case, in the first one here, we show is delta j equals negative 1. Let's look at the second one. This one is j equals 10 to j equals 9. So 10 to 9, again, delta j equals negative 1. And let's look at this one is 9 from 9 to 10. Again, negative 1. So all these transition is delta j belong to delta j equals negative 1. So delta j negative 1. And so it's a combination delta n equals 1, delta j equals negative 1. So both vibration rotation obeys the selection rule. Now let's look at the right side. So let's look at this one is from j equals 9 to j equals 10. So here delta j equals positive 1. And let's look at this one is j from 8 to 9. Again, delta j equals positive 1. So all these lines transition belongs to delta j equals positive 1. Okay. Now here is the shape of the absorption. Again, this one is from 10 to 9, 9 to 8, 8 to 7. So all these absorptions, okay, are these lines absorptions. They are delta j equals negative 1, and these absorptions we call P branch. And the right side these are the absorption between delta J, J from 9 to 10, 10 to 11, so they are delta J equals +1. So these are called the R branch. Now, what's about the center? There's a missing line here, and this is due to the transition from 0 to 0. Okay, and the 0 to 0 against the selection rule, because delta J has to be positive -1. So from J to 0 of first vibration to J equals 0 to the second vibration, and that delta J is 0 and against the selection rule, so it's forbidden. It's called Q branch, but it's forbidden, and therefore you don't see it. Okay, and all these results predicted by quantum mechanics, but also confirmed by experiments. So the chemistry major student will have a Pchem lab experiment that we are going to perform HCl, okay, diatomic molecule infrared absorption spectroscopy, and there you will see all these absorption lines, and you will count this delta J, and you will measure the frequency absorbed, and you will calculate the bond length, and you will calculate the force constant of this molecule. In the last slide, we showed that molecules vibrate and also rotate. So when we do infrared absorption, it's not just because of the vibration. Molecules also rotate, so it's accompanied by the rotation. So then in this slide, we are going to show you some equations. And so the energies now is a combined vibration and the rotation. And in this equation, we ignore enharmonicy. So the first term is due to the harmonic oscillator vibration. And the second term, we ignore the bond distortion. So it's only due to the rigid rotor rotation. Okay. And for the P branch, okay, these are the P branch. The delta J is -1. But don't forget, the delta V rotation of vibration is +1 from 0 to 1. So when we calculate the transition, we should use V +1 minus V. So that's the delta V is +1, but the delta J is -1, so J -1 to J. Okay, and plug in to this equation. So V +1 goes to here, J -1 goes to here, and then minus the other equation using V and J. So if you do that, the equation is this one. And so the P branch theoretical prediction is natural frequency minus 2Bj. B is the rotational constant. Okay, so if you know rotational constant, you know natural frequency of the vibrator, then you can predict the frequency in the P branch, which is determined by J contour number. And similarly, we calculate R branch. Okay, so in R branch, delta J has to be positive, and the delta V is still +1 because it still belongs to 0 to 1. Okay, delta J is still positive, and therefore you calculate is from V +1 minus V. Okay, but the J is J +1 to J, and therefore the answer, final solution, is the natural frequency plus 2Bj +1. So again, we need to know the rotational constant, we need to know the vibration, natural frequency, and we can predict the R branch. In the experiment, we actually measure this R branch, V branch. So we find those absorption frequency, and then we can calculate the natural frequency. We can calculate the bond rotational constant, which also give you the bond length. And the Q branch delta J is 0, and so that's forbidden in this in many cases. In this chapter, we apply the Schrodinger equation to different systems. The first is the pi electrons in a molecule, and we assume the pi electrons can move freely inside the molecule but cannot get out of the molecule, and this is called a particle in a box model. And combined with a boundary condition, we show that only certain energies are allowed, and this is called quantization. And the allowed energy is calculated by a quantum number n squared, Planck constant squared, divided by 8ma squared. A is the box length, and for pi electron molecule, and that's the length of molecule where the electrons can move freely. And so the energy spacing is not equally spaced according to this equation. And when we calculate the interaction with light, we need to find the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And so highest occupied orbitals are the orbitals with electrons, and the lowest unoccupied molecular orbital is the first orbital doesn't have electron. And this separation determines the frequency of light. Our calculations show that for pi conjugate system, and this falls in UV visible range. Now, when we look at study the vibration of chemical bonds, we assume the vibration obeys Hooke's law, and that's called a harmonic oscillator. And solution of Schrodinger equation again give you certain allowed energies. The energy is determined by a quantum number V, which can be 0, 1, 2, 3, 4. And the energy is also determined by the natural frequency that comes from the classical physics, calculated by 1 over 2 pi square root k over mu. So the energy is determined by force constant and by reduced mass. And the energy separation is equally spaced. And therefore, when you do absorption of light, only one frequency will be absorbed, and that frequency falls in infrared. Theoretical prediction, the frequency equals natural frequency. And therefore, if we can measure the frequency of light absorbed by vibration, which is in infrared, then we can calculate the force constant. And the force constant is a measure of the strength of the bond. For rotation, we assume the bond length doesn't change. And this is called a rigid rota. And the solution of Schrodinger equation give you two quantum numbers. So the wave function is determined by two quantum numbers, the angular momentum quantum number and the magnetic quantum number. Angular momentum quantum number also determines the energy of the system. And so the equation of the energy is determined by quantum number L, but also determined by the moment inertia, which is related to the bond length. All right. So if we can measure this energy, we can calculate the bond length. The energy for rotation is not equally spaced, and therefore we predict when we do absorption, you should see many absorption lines. And in fact, the absorption lines are equally spaced. Okay, and the separation between the absorption lines is 2bc in hertz or 2b in inverse centimeter. And this absorption frequency falls in microwave for pure rotation. So if we do microwave absorption, we should see these absorption lines, and we can find the B constant. And from B constant, we can calculate the radius or the bond length of the molecule.